So I've got this simple teleportation system here, and I'm going to show you how to make it. It gives us this nice curvy indicator that turns green when we can teleport and turns red when we can't teleport. So let's get into it. So this is all done on one script on one game object. Let's hop into the meat of that script while your attention span is still alive. Mostly in this try to get teleport target function. And we can see here we have a big for loop that contains a bunch of physics.raycasts. Basically what we're doing here is we're starting at a position, we're casting out in space, seeing if we run into anything. If we don't, we start over at that new position, we angle downwards a little bit, cast out in space again, still don't hit anything, keep repeating, cast out, change downwards a little bit until we hit something. I'm gonna hop back into the scene real quick, just so you can visually see better how that works and it'll make a little bit more sense. Then we'll come back and go through every line of this code. So this is just a line renderer, just a visual indicator, not the actual physics casts. We can't see those, but they are going exactly where this line is going. And you can see it goes out for a little bit, then it changes its angle slightly down, goes out again, does the same thing and repeats. And we do that over and over again and make a curve. To make a nice smooth curve, we just do smaller line segments with less angle change. Let's start from the top. We're just including the Unity Engine namespace, and then I put this in my own custom namespace so it doesn't conflict with anything. And then here we've got a small number of class variables. The first one is just the input that I've decided to use, which is the joystick on the Oculus. But you can do this with any device. Next is the line renderer that indicates where our rays are being cast, which I've just named laser. The next is the number of steps we want to take. We do want to cap this because we don't want, for example, if we're pointing out into space where we're not going to hit anything, we don't want it to just go for infinity. Then we have the distance that we want each segment to be cast out in space, and then an amount of drop per segment so we can control how sharp the curve is. We're keeping track of a couple transforms in the scene. The head, which is whatever is being tracked by the device, and then the camera rig. As I'm sure you know, we can't move the hands or the head of the player in Unity directly. That position is determined by where the track device is in space. But we can move the camera rig that is the parent of those game objects. We have a collision layer here. For example, you want to be able to teleport on the ground but not onto walls. We have a target position that's going to be where the raycast hits a valid teleport location. And we have a bool target acquired, which I was just starting with at false, and that tells us whether we have a valid target that we can teleport to or not. In Awake, we just set the positions in the line renderer indicator to the number of steps we're going to have so that we don't have to set that separately in the editor. And then here in Update, we're actually keeping track of the player's inputs. If they push the stick up, goes greater than Y, then we want to try to get a teleport target. And this is where we're going to display the line renderer and shoot out all our raycasts. First thing I do is just set target acquired to false just to be safe. We don't have a target acquired, but at the end of the frame we're going to run through all this code, and if we do get one, we'll set it to true when we get it, but for now we're just keeping it false. Declaring a raycast hit. Declaring a vector3 origin. This is going to be the origin of each raycast, which will change as we go through our steps, but we're starting just at the position that this game object is at. Now we start this for loop, which is the big show here. Each time we iterate, we need to figure out the direction we're going to shoot the ray out in. And that's going to change every time. And that's where this vector3 offset comes into play. We start with the forward axis of the game object that this is on. We add to that vector3.down, which is always 0, -1, 0 in world space. We multiply that by drop per segment, and then we multiply that by I. For example, at the beginning, the very first raycast, I is going to be 0. We don't want it to be pushed down any at all. We want it to just come out at the angle it's at. But as I increases, as we take more steps, we want it to be pointing downwards more and more so we get that nice curve. We're going to normalize that vector because after a lot of steps, this is going to be larger than it was at the beginning because I is growing, and we want that vector normalized so it's just at a distance of 1. And then we're going to finally multiply that by our adjustable variable laser segment distance. This can be a little bit confusing if you're new to it, but a physics raycast casts a ray out in space, and then returns a bool. It's true if it hits something and it's false if it doesn't. So for now, ignore all this stuff. If we hit something, we do this, but if we don't, else we do all this stuff. So let's look at our raycast. We start at a position of origin, we shoot out in the direction of offset, we out some information, hit. So for example, we can tell where in space we hit, and the distance this ray gets casted is our adjustable variable. So if we hit something, this is what we want to do. This code here just goes through all the remaining laser positions and sets them to the position that is hit, just so they're not flying off crazy in space. Then we determine, is the thing we hit something like the ground or whatever we've set to terrain? And is it something we want to teleport to? So we check if it's equal to this collision layer we determined up earlier. If it is something we can teleport to, we set the laser's color to green. We set our target position to the point in space that we hit dot point, and we say target acquired equals true. Yes, good, we have a target. Now we say return. We came into this try to get teleport target function, and we got one. So return, we're out. Else, if we hit something that is not on the correct collision layer, we're going to set it to red to indicate to the player you can't teleport here. And again, we're going to return. We're saying we try to get a teleport target, and target acquired equals false. This stays false all the way down, and we return. No target, what you hit is something like a wall or a ceiling, not somewhere you can teleport. But skip all that, and let's say we tried to do this raycast. If we hit it, we do that, but we didn't hit it, so else we're gonna do this stuff. Set a position of the line renderer so that it displays correctly. And then we need to modify the position that the next line is going to be cast. So just add the offset vector to the current origin position. And that will change the origin position forward so that we can use it for the next position to cast a ray from. So if we get all the way through this entire loop without ever hitting anything, let's say you just shoot it out into space, or you have a small number of line segments so it curves up and comes down but isn't able to hit anything. We haven't hit anything, we have no target position. We're going to set the laser color to red. And still, target acquired is false. Well, let's come back up to the update method. Let's say we did get a target and we've released the stick, it's gone back to the center, so it's less than 0.2. Then let's teleport. If you try to teleport again and you don't actually get a new target, and you reuse that target, that would be weird. So I'm just setting target acquired to false so that we have to go back up into try to get teleport target and get one. Then we just reset the laser visually, reset the line renderer. And here we actually move the player. And this part I think might need a little extra visual explanation. So you probably already know that we can't move the player's left hand or the player's head position in Unity by script. That's going to be determined by where they are in space, tracked by the device. So we don't want to move that. What we do move is the camera rig that everything else is parented to. So I drew this little diagram. We have the parent position and the player's position, and you notice there's an offset. So how do we keep that offset as we move to a new position? When I'm breaking down a little programming problem, I like to declare, what do I want? What is my desired output? And what inputs do I have to work with in order to create that output? So our desired output is a position in space for the parent that places the player at the desired teleport location. So they want to teleport over there, and you need to get them there, but you can't move them, you need to move the parent. But you can't move the parent to the teleport location because then their offset would place them away from the location they actually wanted to teleport to. You need to put the player at the target location without moving them directly. The inputs we have are the current player location, the parent location, and the targeted teleport location. The way we turn those inputs into the output that we want is to take the difference in position between the target and where the player is currently, and instead of adding that to the player, add that to the parent. That's not going to move the parent to the target location, but it will move the player to the target location because the player is offset to the parent. So that works for the horizontal dimensions, the X and the Z dimension, because we want to teleport the player's head exactly to the target in those horizontal dimensions. But we don't want to do that in the vertical or Y dimension. We don't want to teleport the player's head into the floor. So for that, it's a little bit different, and we actually do teleport the parent position to the target position. So when you're trying to get a vector that goes from somewhere to somewhere, just remember this: subtract the one you're coming from. And in code, that looks like this. We get our offset vector by taking target position x minus head position x, target position y minus rig position y, and target position z minus head position z. Then we just add that offset to the current rig position. Now let's take a quick look at how we assign those serialized fields in the scene. So here on the script, I just chose primary thumbstick. That's the stick for the left hand, which is where I have this parented to. The laser is a line renderer that I already have on here. And this is important, actually. You got to make sure you check use world space. That must be checked, otherwise the positions that are assigned earlier are going to be pretty weird. They're going to be in the local space of the laser, and they're not going to be correct. So make sure you set that to world space. Also, for the color to change from green to red, you've got to set a material with a UI shader or some other shader that can be manipulated by this color field here in the line renderer. This laser steps, this is a chunky version here that I had earlier, so it's set to 20. The distance is 1.5 and the drop per segment is 0.4. Those are all quite large. Just increase the number of steps and decrease the distance and the drop per segment in order to get a nice smooth curve. The head is just whatever device is tracking the head. Here I'm using Oculus and the OVR plugin, so it's the center eye anchor. And the camera rig is the stuff that it's parented to, so I'm just using OVR camera rig. And the collision layer is set to 9 because I have 9 as ground, as an area that the player can teleport around on. So you just child this to one of the hands you want it to work on, and that's that. So I hope you were able to learn something from this tutorial, and maybe you can use this in one of your projects. I personally made this because I was just frustrated with how bloated and everything felt in the Oculus VR plugin for Unity. I understand they have to do that so that it's really flexible and people can use it for all kinds of stuff, but felt like it was taking more time and it was more confusing to try and use theirs than it was just to make it myself. So I just wanted to share this with anybody else that's watching and needed help with it. If you want to see more straight to the point tutorials or other ridiculous VR content, go ahead and subscribe. I'm trying to make more videos about VR and all kinds of stuff like that. So hope to see you again. Thanks for watching.